In this video, we're going to discuss the Nernst equation. The Nernst equation is an equation that is used to calculate the cell potential for a redox reaction when the concentrations are non-standard. So if you have a redox reaction that you perform and the concentrations of reactants or products are anything other than 1 molar, then we can use our Nernst equation that you see here to calculate our cell potential E. Now what I'd like to do in this video is examine how we derived this Nernst equation and also how to use it to calculate our cell potential. So if you recall previously from our discussion of thermodynamics, we discussed how to calculate the free energy change, delta G, for a process that occurs under non-standard conditions. And we came up with this equation where delta G is our free energy change under non-standard conditions. Delta G naught is the delta G value for the standard conditions. R is our gas constant, T is the temperature in Kelvin, and Q is our reaction quotient, which allows us to use our concentrations that are non-standard. Now we've also came up with another equation when we were discussing redox reactions. We showed how the free energy change, delta G, for a redox reaction is related to the cell potential. So we also have discussed these equations. Delta G is equal to negative N Fe, or delta G standard is equal to negative N Fe standard, where of course delta G is our free energy change, or delta G naught is the standard free energy change. N is the number of moles of electrons transferred. F is Faraday's constant, and E is the cell potential, or E naught is the standard cell potential. Well, we can combine these equations to help us get the Nernst equation. So let's look back. Here's the equation that we use to calculate delta G under non-standard conditions. But instead of using delta G, let's substitute in negative NFE for delta G, and for delta G standard, we can substitute in negative NFE standard. So we're just going to replace or write our free energy change in terms of cell potential or in terms of standard cell potential. So if we do that, our equation should look like this. Again, we've just replaced delta G with negative NFE, or delta G standard with negative NFE standard. We've combined those equations that we just discussed. So now let's take the equation that we just derived here and let's manipulate it just a little bit. Let's divide through by negative NF. Again, N is the number of moles of electrons transferred, F is Faraday's constant. So let's divide our equation through. If we do that, our negative NFE, or our negative NF, cancels here, and it cancels here. So we're left with E standard. As you can see here, we end up with E, our cell potential, is equal to the standard cell potential. We divide it through by negative NFE, so we minus RT divided by NF natural log of Q. Again, we've just manipulated this equation slightly, so now we have it in terms of cell potential and standard cell potential. Now we can use this equation to calculate the cell potential under non-standard conditions. So this is a perfectly good equation that we can use to calculate the cell potential under any non-standard conditions. But the Nernst equation goes a little bit further. It simplifies it just a little bit. So let's keep going. So if we assume standard temperature, 298 Kelvin. So let's assume our temperature is constant, that we're performing this reaction at 25 Celsius or 298.15 Kelvin. Well, R is a constant. Now our temperature, we're assuming that to be 298 Kelvin. Faraday's constant is obviously a constant. So we can multiply all of these and we come up with this. So our equation simplifies a little bit, assuming the temperature is 25 Celsius or 298 Kelvin. Standard cell potential, the cell potential is equal to the standard cell potential minus 0.0257 volts divided by the number of moles of electrons, natural log of Q. And again, this number here, the 0.0257, came from multiplying RT and dividing by F. So check, you can plug that in and confirm that that is the case. And our units here would be in volts. So let's take our equation here, and often instead of a natural log, let's express that as a logarithm. And the reason we do this is because the Nernst equation, or this equation that we're about to derive, is often used to calculate the pH of a solution. Of course, the pH is the negative log. So we're just going to change this from natural log to a log base 10. And when we do that, our 0.0257 becomes 0.0592. And again, that's the correction factor between natural log and a logarithm. So again, now we have derived this equation, and this is the Nernst equation. And as we showed you at the beginning, it allows us to calculate the non-standard cell potential when we have concentrations that are, again, non-standard. So the Nernst equation is used to calculate the cell potential at non-standard concentrations. But as we mentioned before, to use the Nernst equation, the temperature must be 25 Celsius. Otherwise, we have to go back and use an earlier version of this equation. But generally, most redox reactions occur at this, or we perform them at this temperature. So this is a good assumption. So let's take a look at this problem. Consider a galvanic cell which uses the following reaction. See if you can calculate the cell potential for this reaction at 25 degrees Celsius if we have the following concentrations of ions. So let me put up a table that you may need, and then pause the video and see if you can solve the problem. Okay. So go ahead and pause the video. So the first thing I recognize here is that I'm asked to calculate a cell potential. I also recognize that my concentrations are non-standard. Not everything is 1 molar. So I need to know which equation to use. This would, of course, be the Nernst equation. Allows me to calculate the cell potential under non-standard conditions, under non-standard concentrations. So the first thing I'm going to calculate is my standard cell potential. Looking at my chemical equation, I can see that copper is undergoing oxidation, where the iron from +3 to +2 is undergoing reduction. It's gaining electrons. So if I look back at my table, I get the half reactions for iron and copper, and I'm going to copy down the standard reduction potentials for both. So I have the standard reduction potentials, but as the equation was written, I can see that the copper was undergoing oxidation. So the copper, I have to flip the reaction and also change the sign in order to make this a standard oxidation potential and this the standard reduction potential. Okay. Now also, I add these two together in order to get my standard cell potential, which is 0.43 volts. So E oxidation plus E reduction gives me the E cell standard. And also, if I add these two reactions together, before I add them together, I notice that the copper is losing 2 electrons, where the iron half reaction was only losing 1. So in order to balance these half reactions, I had to multiply this one by 2. Now that's not necessary to get your standard cell potential, but I do need to figure out the number of electrons transferred. So I can see that copper is losing 2, and in order to get them to balance, I have to multiply this by 2 in order to get the iron half reaction to gain 2. So here, this tells me that there are 2 moles of electrons being transferred, 2 being lost and 2 being gained on the iron half reaction. So I need that information also. So now, back to the Nernst equation. I know my E standard, my cell potential standard, and I also know that there are 2 moles of electrons being transferred, N equals 2. And I got that from my 2 half reactions, my balanced half reactions. So I plug those values in. Here's my E standard cell, my N equals 2, and now I need to solve for Q. Q is going to equal the concentration of products, concentration of copper, aqueous, and the concentration of aqueous iron 2 plus squared, because we have a 2 coefficient, we have to square that, divided by the concentration of aqueous iron 3 plus, again, squared. We do not need copper in our equilibrium constant or our Q equation because copper is a solid. We do not include solids or pure liquids. So now I just need to plug in the values that are given, and now I can solve for the E value. So my cell potential under these non-standard conditions comes out to be 0.25 volts. So remember your units, and be sure that you can recognize when to use the Nernst equation, and then of course be able to correctly use it.